Usually when we look at a digital photo, there's this expectation of a bottom floor. Like you zoom in far enough and eventually the illusion just breaks.
Right. You just see the pixels.
Yeah, exactly. The pixels. Little discrete blocky squares of color. And I think it's a comforting assumption we make about the physical world, too.
It really is. We want things to have a foundational layer, a baseline where the complexity stops and, the math gets simple and everything is built out of finite, indivisible little blocks.
But that pixelated bottom floor might completely fall right out from under us today, because we are diving into a highly technical theoretical physics paper titled Empirical Proof for Infinite Fractal Descent.pdf.
It is a dense one, but incredibly rewarding once you get into it.
Definitely. And our mission for this deep dive is to bypass all that dense academic jargon and ask you, the listener, a genuinely paradigm-shifting question. What if reality is a bottomless, infinite fractal?
Meaning, what if, from the furthest edge of the cosmos down to the tiniest quantum particles, there are just no fundamental building blocks at all?
Okay, let's unpack this, because we are not just doing a standard physics summary here. This is a completely new lens through which to view reality itself.
Exactly. So the standard model of physics basically assumes that space-time is a smooth, continuous fabric.
Right.
But the infinite fractal descent framework, or IFD, argues that reality is actually built on recursive, self-similar geometries. Dimensional feedback loops, essentially.
Meaning the structural pattern of the universe repeats infinitely at every possible scale. Which is just wild to think about.
It is.
So to really grasp if the universe is a fractal, we have to start by zooming out as far as physically possible, right? We're talking about the distribution of entire galaxies.
That's right. And the standard cosmological model assumes that if you zoom out far enough, the universe becomes perfectly smooth and homogeneous.
I like to think of this standard model's universe like a blended smoothie. You throw in strawberries, bananas, kale, and it looks totally chaotic inside the blender.
Right. Chumps everywhere.
Exactly. But once you hit puree and you step back, it's just a perfectly uniform pink liquid.
Mathematically speaking, in a three-dimensional space, a perfectly smooth, random distribution of matter should have a fractal correlation dimension of exactly 3.0.
And physicists denote that as D2.
Yes, D2. That perfect 3.0 represents a space that is completely and uniformly filled. It's the holy grail for the standard model because it's the point where all the localized chaos supposedly averages out into that smooth pink liquid.
But IFD suggests the universe is absolutely not a smoothie. It's more like a chunky soup.
A very chunky soup.
Right. No matter how far you zoom out, you never get a smooth liquid. You just keep finding highly structured chunks repeating the same patterns. And apparently the empirical data from modern astronomy is backing up the chunky soup theory.
It really is. Over the past 2 decades, massive redshift surveys like the SDSS and EBOSS quasar catalogs have been desperately trying to find that exact scale where the universe finally smooths out to a perfect 3.0.
But they can't find it.
No. At massive scales, like 80 to 150 megaparsecs, the dimension stubbornly hovers around 2.81 to 2.9.
Okay, let me push back on this for a second, though, because we were talking about a difference between 2.81 and 3.0. That's a fraction of a decimal.
It seems tiny, yeah.
Could this 2.81 measurement just be a rounding error? Like maybe our telescopes just aren't powerful enough, or there's, I don't know, some interstellar dust skewing the math. Why are scientists so hung up on missing that perfect 3.0?
Well, it's a natural assumption, but aggressive corrections have been made for survey geometry and observational constraints. That fractional gap just remains. What's fascinating here is that this persistent margin, that missing 0.19, represents what physicists call residual multifractality.
Residual multifractality.
Exactly. It means that what we currently think is the scale of homogeneity, like the supposed edge of the smoothie, is an illusion. It is likely just a tiny inflection point in a super-horizon fractal hierarchy.
Meaning our telescopes simply aren't big enough to see the next layer of the pattern. Like we think we've reached the end of the puzzle, but we're really just looking at one piece of a much larger fractal shape.
Precisely. And we see this structural bias even in the cosmic microwave background, which is the oldest light in the universe.
It's essentially the baby picture of the Big Bang, right?
Right. And the standard model predicts this radiation should look like random television static, just pure, unstructured noise.
But the Planck satellite data revealed massive, unexplained cold spots and structural asymmetries.
Which standard physics really struggles to explain.
Yeah, and the source paper points out that when you run this cosmic baby picture through a fractal model called the REDS framework, those anomalies aren't random at all.
Not in the slightest. The temperature fluctuations have a specific fractal dimension hovering around 2.0, and the residual cold and hot spots are perfectly structured, actually scaled by the golden ratio.
Which is just mind-blowing. So the early universe wasn't just expanding randomly, it was physically imprinting a recursive fractal signature onto the very fabric of space.
It implies a dimensional feedback process. The universe was organizing itself geometrically from the very first moment.
Okay, so if the absolute biggest things in the universe, like galaxies and the cosmic microwave background, are structured as fractals, does this structural memory scale down? Like, what happens when we zoom all the way past the everyday world down into the absolute microscopic material that builds it?
Well, that brings us to the subatomic world, and a concept introduced in 1976 by physicist Douglas Hofstadter.
Oh, Hofstadter's butterfly, right?
Yes, he predicted that if you took electrons, confined them in a flat, two-dimensional crystal lattice, and subjected them to a strong magnetic field, their energy levels wouldn't shift in a smooth, predictable curve.
They do something weird.
Very weird. The energy spectrum would split into a highly complex recursive fractal. If you graph the allowed energy states, the visual output looks exactly like a self-similar butterfly.
Hofstadter's butterfly. It's a beautifully poetic name. But the paper notes that for decades, this was deemed completely impossible to actually test in a lab.
Right, because to see the butterfly in a normal atomic crystal, you'd need a magnetic field of around 10,000 Tesla.
Which is absurd. For context, an MRI machine is usually around 1.5 to 3 Tesla. 10,000 Tesla would essentially rip apart whatever laboratory you built a machine in.
Exactly. So it remained a pure mathematical curiosity until quite recently.
When materials engineers figured out how to physically alter the grid, the electrons were trapped in.
Yes, they took two incredibly thin sheets of carbon atoms, basically graphene, and stacked them. Then they twisted one sheet at a very specific magic angle.
Okay, let me try to visualize this for everyone. Imagine taking two pieces of chain link fence and laying them on top of each other. If you perfectly align them, you just see the normal diamond-shaped holes.
Right.
But if you twist the top fence just a little bit, a massive new geometric pattern suddenly emerges from how the wires overlap.
That new, larger overlapping pattern is called a Moore superlattice. By creating that larger artificial cell size in the twisted bilayer graphene, the magnetic field required to reveal the fractal dropped.
From an impossible 10,000 Tesla down to just a few.
And when researchers ran the experiment, they directly visualized the fractal gaps. Google even simulated it using interacting photons in 9 superconducting qubits. The energy landscape of those electrons was a strict recursive fractal.
Wait, okay, you're losing me a bit as we get deeper into the quantum side, specifically with a concept the paper calls wave function scarring.
No.
Because my understanding of quantum mechanics is that it is fundamentally blurry.
It is very probabilistic, yes.
Right. It's a cloud of pure chaos, where you never really know where a particle is until you look at it. So if it's pure probability, how does a rigid geometric scar form in the middle of it?
That paradox is exactly what makes this discovery so groundbreaking. Let's ground it in classical physics first.
Okay.
If a system is purely chaotic, imagine a perfectly bouncy ball thrown into a wildly asymmetrical room. That ball will bounce off the weird walls and eventually cover every single inch of the room's airspace equally.
The ball has no memory, so it just ends up going everywhere over time. Total chaos.
Right, and that uniform spread of chaos is called ergodicity. But in the quantum realm, the probability density doesn't always spread uniformly like the bouncy ball. It forms scars.
Scars?
Yeah, think of it like a worn-in dirt path in a really busy city park. Even though hundreds of people are walking randomly in different directions through the grass, the physical geometry of where the gates and fountains are forces people to cross certain trajectories more frequently.
Oh, I see. So over time, a permanent visible path is worn into the grass.
Exactly. The random quantum probability carves a permanent high-density racetrack into the chaos. And when researchers measured these high-density ridges along unstable periodic orbits, they found the scars possess specific measurable fractal dimensions.
So the universe utilizes these recursive probability topologies to maintain stability and structural memory right at the boundary where deterministic physics should dissolve into total chaos. The geometry literally stops the system from falling apart.
That is exactly what IFT proposes, yes.
If the universe is using these geometric scars to keep quantum chaos from dissolving, does that same stabilizing trick apply to highly complex living things? Let's bring this directly to you, the listener sitting in your chair right now or taking a walk while listening. How does infinite fractal descent physically shapes the human body.
Biology is actually the most accessible laboratory we have for analyzing fractal structures. It forces us to look at the mechanisms of survival.
Here's where it gets really interesting. Because in 1932, a scientist named Max Kleiber noticed a bizarre rule governing metabolism. It's called Kleiber's law.
A classic puzzle in biology.
Right. Basically, the amount of energy an organism burns scales to the 34 power of its body mass. And this holds true across incredibly vast categories of life. From a tiny mouse to a massive elephant, they both follow this exact same 34 power law for how they burn energy.
But simple geometry dictates that shouldn't happen. If you just scale up a 3D object, basic surface area to volume math insists the metabolic rate should scale to the 23 power, not 34.
So this discrepancy was a massive biological puzzle. Why was life constantly hitting 34 instead of 23?
The answer, proven by the WBE model, lies in how things branch.
Yeah, think of your cardiovascular system like an impossibly huge postal delivery network in a sprawling metropolis. Your heart is the main post office, and the blood cells are the delivery trucks.
That's a great way to picture it.
The only mathematical way to ensure every single house in that city gets a package, without the delivery trucks running out of gas driving across town, is to build the roads in a repeating, self-similar fractal pattern. Big highways branch into smaller roads, which branch into neighborhood streets, which branch into driveways.
Right, and if we connect this to the bigger picture, the underlying physical mechanism here is thermodynamic efficiency. The universe is fundamentally lazy. It wants to dissipate energy using the absolute minimum amount of effort.
So the fractal network minimizes the friction and the energy required to transport blood.
Exactly. And because this branching network is so perfectly space-filling, it creates a fascinating mathematical reality. It essentially makes our biology operate in 4 dimensions when it comes to energy consumption.
Wait, I am a 3-dimensional object.
Yeah.
How can my biological network operate in 4 dimensions? That sounds like sci-fi.
It does, but it's because the fractal branching is just so dense, it fills the 3-dimensional volume of your body so thoroughly that mathematically the network acts as an extra spatial dimension for transport.
Oh, wow. So the 34 exponent in Kleiber's law is literally the ratio of a 3-dimensional volume operating within a 4-dimensional fractal topology.
You got it. The fractal geometry essentially bends the rules of 3D space to squeeze out maximum efficiency.
And this isn't just happening with our blood supply either. The physical wiring of the human brain, the connectome, faces an incredibly extreme biophysical trade-off. It needs to minimize metabolic cost while maximizing signal speed, all crammed inside a very small skull.
And when neuroscientists analyze the structural wiring of the brain, they find it exists in an extended critical phase. It heavily utilizes multifractality, yielding a fractal dimension of roughly 0.7 to 0.8.
So the physical folding and connectivity of your neurons are utilizing optimal fractal descent to compress complex information processing into a confined physical space.
Exactly. These fractal geometries in biology aren't evolutionary accidents. They are absolute physical necessities imposed by the thermodynamic laws of spacetime for optimal energy descent.
The way the universe builds structures to stabilize quantum chaos is the exact same mathematical method your body uses to pump blood and fire neurons. It's one universal rulebook.
Which is a beautiful concept.
It really is. And it logically leads to a massive claim in the source material. If this fractal framework is the true governing rule of reality, then it should logically be able to solve the biggest, most glaring mysteries that traditional physics currently gets completely wrong.
And there are definitely some glaring mysteries. One of the greatest embarrassments in modern theoretical physics is what's known as the vacuum catastrophe.
The vacuum catastrophe sounds ominous.
It is for the math. When standard quantum field theory tries to predict the energy density of the empty vacuum of space, it assumes the vacuum is a boiling soup of virtual particles constantly popping in and out of existence. Using that model, it predicts a vacuum energy value of 10 to the power of 113 joules per cubic meter.
But when astronomers actually measure the expansion of the universe to see how much energy is really out there in the vacuum, the measured value is 10 to the power of -9.
Right. It is a 120 order of magnitude error.
That is just absurd. Let's put that in perspective for a second. If you were off by 120 orders of magnitude on your taxes, you wouldn't just get audited. The IRS would have to invent an entirely new system of mathematics just to comprehend how wrong your form was. It is an unfathomable miss.
It really highlights that something is fundamentally broken in the standard model.
So how does the infinite fractal descent framework fix a math problem that broken?
It fixes it through the Unified Fractal Quantum Field Theory, or UFQFT. It completely abandons the idea that empty space is a boiling soup of random particles.
Okay. Instead, the vacuum is modeled as a continuous, structured geometric ocean, like a dark energy ocean.
Yeah.
And it possesses a specific, non-integer fractal dimension of pi squared divided by 2.
And in this geometric ocean, the concept of gravity completely changes, right? Because standard physics teaches us that gravity is like a heavy bowling ball sitting on a rubber sheet, curving the space around it.
Right, but the IFD framework says gravity isn't curved space-time at all. It's simply fractal compression.
Fractal compression. Okay, explain that.
Think of empty space not as a flat, empty stage, but as a dense, tightly compressed geometric sponge. When mass or energy moves through this fractal vacuum, it compresses the local geometry. The space naturally tries to spring back, to decompress and restore its geometric symmetry. That physical restoration, that geometric pushback, is what we actually feel as gravitational attraction.
It's an incredibly elegant visual. Instead of inventing invisible forces or dark matter to make the math work, it just relies on a universal mathematical constant. It's just the physical geometry of space wanting to relax back into its natural shape. And relying on that simplifies physics and removes the need for ad hoc patches. In fact, the paper details how this geometric approach was put to the test in a high-performance computer model called the CODES simulation framework.
Right, and for decades, standard cosmological simulations have relied heavily on dark matter, because there just isn't enough visible mass in the universe to hold spinning galaxies together.
So physicists basically invented dark matter, an entirely invisible substance that doesn't interact with light, just to provide the extra gravity needed to hold things together.
But we've never actually seen a single particle of dark matter.
Never.
So the code simulation did something radical. They just deleted dark matter from the code entirely.
They ditched it completely. Instead, they simulated the formation of galaxies using pure geometry, specifically using what they call recursive prime resonance intervals.
The best way to understand prime resonance intervals is to think of musical chords.
That's a perfect analogy.
When you play certain frequencies together, the sound waves overlap and reinforce each other, creating a stronger structural resonance. The simulation basically applied this concept spatially. They placed nodes of energy at these repeating, overlapping geometric intervals.
And the result was staggering. The simulation perfectly recreated the cosmic web. It organically yielded 249 distinct galaxy clusters with an extreme directional preference.
An anisotropy ratio of 7.59, right?
Yes, which perfectly mirrors the long-range galaxy structures we actually see through our telescopes, far better than standard stochastic models do.
So it generated the exact binding effects of dark matter without needing a single invisible particle. The overlapping structural resonance of the fractals naturally held the simulated galaxies together.
It proves that if you apply multi-scale recursive rules to a simulation, macroscopic cosmic structures naturally emerge as the path of least resistance.
So what does this all mean? Let's bring the pieces together. What this deep dive reveals is that the universe is fundamentally driven by thermodynamic efficiency. It wants to move energy as easily as possible.
That's the core of it, yes.
And from the golden ratio echoing in the primordial microwave background, to the quantum butterflies hiding in atomic lattices, to the 4D math dictating the blood pumping from your heart fractals, are the ultimate mathematical path of least resistance.
It's a singular mechanism operating at every conceivable scale, which is why the ongoing search right now is for a universal fractal constant.
One measurable number that ties the macro and the micro together. And researchers are finding evidence of it in the most wildly disparate places.
It's an incredible finding. They recently compared the violent impact mechanics of the macrocosmos to the fluid dynamics of microscopic biology.
Right. First, they measured the topographic dimension of massive meteorite impact craters on the moon. The physical roughness and mass displacement of a giant lunar crater has a fractal dimension ranging from 2.4 to 2.6.
And then they measured the spatial distribution of microscopic cellular pores. You know, the tiny geometric doors that regulate how ions pass in and out of a biological cell membrane.
And the fractal dimension of those cellular pores averages exactly 2.57.
2.57.
A number that falls perfectly inside the 2.4 to 2.6 range of the moon craters. The interface of a massive meteorite violently smashing into the lunar surface and a tiny ion gently passing through the membrane of one of your cells are mathematically identical.
The universe manages the transfer, rupture, and dissipation of energy using the exact same geometric operator, regardless of whether it's the size of a planet or the size of a protein.
It strips away our arbitrary human categorizations of size and scale, revealing an underlying unity to reality that goes far deeper than discrete particles or smooth fabrics of space-time.
It really makes you reconsider everything.
It does. Which leaves us with a final provocative thought we want you to ponder today. The next time you look out your window at the fractal branching of a tree, or you look down at the branching veins on the back of your hand, consider the mechanism at play. If the exact same mathematical rules dictating the birth of galaxies, the scarring of quantum fields, and the violent cratering of moons also dictate the blood pumping through your veins right now, are you truly a separate observer living in the universe?
Or are you just the universe recursively experiencing itself at a very specific fractal scale?
A profound question, and one that absolutely makes you reconsider where the boundaries of the self actually end.
Absolutely.
So much for that comfortable, pixelated bottom floor. Thank you for joining us on this deep dive. Keep questioning, keep zooming in, and we'll catch you next time.